This is the ring, and try to understand from here. So this is the ring and the current is coming like this towards us. And we have to find out the field at this point. So again we will take the same approach. The ring may be supposed to be made up of a large number of very small elements, and I will consider one element of length dl, very small here, and we'll find out the field at P due to this element. Okay, we'll have to take this distance. Okay. Now see, what is the field at P due to this part? Mu naught by 4 pi I dl sine theta upon this distance square. So it's very easy to understand. I'll take it r square plus x square. These are the known quantities. So this distance is this square under root of it. So it is squared, so root gone. Okay, what is the value of theta now? And what is the direction? Two things are to be understood very carefully here. The value of theta, the angle between dl and this length, this vector, and the direction of dv. Now again try to understand. I have taken this dv here and r is this, where I have to find out field at P. So I need the angle between this and this tangent. So it is this. This is this vector and tangent is along the circle. So I need this angle actually. How much is this angle? This one. It is 90 degrees. Try to understand it very carefully. Theta is 90 here. DL is tangential and this is the vector. So you need this angle. Theta is 90. Okay, what is the direction of dV now? To find out the direction of dV, we have to apply either this rule or this one is easier again. I will suggest you to apply this. Current is towards us and this is this vector. Again, see, thumb towards the current and these fingers here, perpendicular to it. This is the direction of the field. So this is outward, the fingers towards the point P and perpendicular to it is the field. So it means this will be the direction of the field. Once you have understood it, now it's very simple. Okay. So theta is 90, I am substituting here only. So theta 90 means sine 90 is 1. Okay. So this is, and this is the direction. If I find out the field due to this element, it will be now current out, no, out, current in. So this, so it will be in this direction. Again, two components of it. So I can resolve this into two components because all the fields will be like this only, perpendicular to this line. So this will be this, then this will be this, and same way. So it will again be sort of cone formed due to all these vectors. And all of them can be now resolved into two parts, one this, and same way this vector, this can also be resolved into two parts, one this, and same way every vector. If one vector is coming like this, one this and one this, same way one will be inward like this. So it has two components, one this, and if you can imagine that these components will be in same direction and one component due to all will be perpendicular to this line. So if I take this as see, we need to give this angle some name, can be anything. If I give it phi, then this is 90 minus phi, this is phi, this will be 90 minus phi. It's not necessary that we give phi this. We can write phi this, then it will be 90 minus phi. It doesn't matter. 90 minus phi is phi, so this will be phi. Understand this now. Phi, this is 90, so it becomes 90 minus phi. And this is perpendicular to this, so this becomes phi. And this will be 90 minus phi because these two are 90 degrees. Okay. So, this will be dB cos phi and this will be dB sin phi. Now if we find out the fields due to all these components, one will be along the axis, due to all, one will be perpendicular. But all perpendicular components will cancel out. For every component we have an equal and opposite, but all these are in the same direction. So it means the net field will be integration of dB cos phi. dB cos phi. Okay. dB cos phi. That will be the net field. Now we can substitute the values here. dB is mu naught by 4 pi IDL upon R square plus X square into cos phi. Let me substitute the value of cos phi now. This is 90 minus phi. Either I can find out sine 90 minus phi, which will be cos phi, or I can take from this triangle directly cos phi. Cos will be base upon hypotenuse. So base is R and this part is under root R square plus X square. Okay. So now this becomes mu naught by 4 pi I dl r upon r square plus x square raised to the power 3 by 2. This is the field. So simplified. Looks complex, but it is not actually. The reason being, x is constant, even r is constant. So all these terms which are looking very complex can be taken out of the integral sign actually. Mu naught I r upon 4 pi r square plus x square raised to the power 3 by 2. All these are constants and we are left with just integration dl. And this we have done earlier also. What is the meaning of integration dl? All dl's added together for a circle makes 2 pi r. So this is 2 pi r. So now the relation is mu naught upon 4 pi 2 pi I r square upon r square plus x square raised to the power 3 by 2. This is the magnetic field produced by current carrying circular loop on its axis. Distance x away, and the direction is along the axis of this field. So if we put a magnetic compass here, it will align itself along the axis. Depending on whether the current is clockwise or anti-clockwise, the compass will be either this or this, but it will be along. Okay, we can simplify this expression further. We can write it in terms of some other quantities. Here, pi r square, it is actually the area of the loop, pi r square. So, I a, this becomes I into a. This is also called magnetic dipole moment. Very important quantity. magnetic dipole moment. So this expression can again be in terms of dipole moment mu naught by 4 pi 2, and we had 2 pi r square I, so it is just 2 pm now, r square plus x square raised to the power 3 by 2. Okay, so this is the field produced due to this. We can have again one approximation. If x is much larger than r, this distance is very large, such that this appears just like a point. So you can remove r in that case, and what it becomes, it is now mu naught by 4 pi 2 pm by x cube. Now if you can recall the expression for the electric field due to a dipole on its axis, it is a similar expression. 1 upon 4 pi epsilon naught 2p by x cube. The constant 1 by 4 pi epsilon naught replaced by mu naught by 4 pi. Here we have magnetic dipole moment, there we had electric dipole moment in the distances. So here this is the magnetic field, particular expression, this is the general expression 2p. And just one more thing I will like to tell. I into A. Current into area of the loop. This is the magnetic dipole moment. For a single turn, if we have n turns, it needs to be multiplied by n times. And same way the expressions for the field also. That field is due to a single turn of the loop. If we have n turns, it should be multiplied by n. This is the magnetic dipole moment. How do we find its direction? This is a vector quantity. And let me tell you how to find direction. Its direction is same as of area vector. But area vector for a loop can be up, can be down. So how we find is, we turn our finger in the direction of current. Thumb will give us the direction of dipole moment. So this is the direction of dipole moment. Okay, turning the fingers in the direction of current. So always perpendicular to the given loop. For this, what will be the direction of the dipole moment? This. So in the direction of the field. Or we can say field is in the direction of the dipole moment. Okay. So this is how we can find out the dipole moment of any current carrying loop, and this is how we can find out its direction. Magnetic field due to a loop on the axis. Again, let me tell you briefly. We can assume that the loop is made up of a small number of elements. We took one such element, then find out the magnitude of the field at this point. Mu naught by 4 pi IDL sine theta upon the square of this distance. This is under root r square plus x square, and that theta is 90, dl and r, this angle. So that becomes 90. Now we resolve this into two parts. And if we find out the fields due to all such components, these components, perpendicular components will cancel out, and all these will be added. So net field will be integration of dB cos phi. We substituted the value of cos phi from this triangle, and then we got an expression mu naught by 4 pi 2 pi n I r square upon r square plus x square raised to the power 3 by 2. One very particular form, if the distance is very large, then it reduces to mu naught by 4 pi 2p by x cube. We got a term dipole moment. This is how we can find its direction, and it is current times area. For n number of turns in the loop, we need to multiply it by n. So that's all in this. Now in next class, I will take a few problems related to the magnetic field due to a circular loop at center as well as on the axis. Thank you.